this video, we're going to be finding something called the Weierstrass factorization of the gamma function. Now, recall that Euler found that the sine function could be written as an infinite product. Well, didn't actually prove this, but this is correct. So the way you find this factorization is you just look at the zeros of the sine function, which is every integer multiple of pi, and then you basically just make an infinite product in the only way that makes sense, and it just so happens to work out perfectly. Now, there is an analogous formula for the gamma function, but it's quite a bit more complicated. It's a specific case of a more general theorem which says that, roughly speaking, if you have any nice function, you can factor it in a way like this, where you look at the zeros of the function and you have a linear factor for each of those. Now, that isn't quite right. You need some adjustment factors, but that's the gist of it. So the analogous factorization for the gamma function, well, it ends up being nicer to look at 1 over gamma for reasons that I'll explain in a moment. You end up with z e to the gamma z times the product over all positive integers of 1 plus z over n times e to the minus z over n. Okay, now where on earth does this come from? Well, we can motivate this by looking at the zeros of 1 over gamma. That will at least get us a good chunk of the formula. So recall that the gamma function is defined in terms of an integral. And for positive integers, it's a shifted factorial function. And in general, gamma of z plus 1 equals z times gamma of z. And we can use this formula to extend gamma to the entire complex plane. So for example, if you have some z value in this strip here, so the real part is between -1 and 0, what you can do is say gamma of z equals gamma of z plus 1 over z. And now gamma of z plus 1 is well defined in that range. So you can apply the integral formula. So if you repeat this, you can extend it to numbers with real part bigger than -2, and then extend it some more until you get the entire complex plane. Well, almost, because you have poles at 0, -1, -2, and so on. Now, those are the only poles of the gamma function because gamma is holomorphic for the real part bigger than 0 because of this integral formula. And then when you do this division by z, or z plus 1, z plus 2, you'll never introduce any poles except at 0, -1, -2, and so on. Okay, so gamma is meromorphic, and the only poles are at 0, -1, -2, and so on. And to make things even better, it turns out that gamma is never 0. Okay, so what does this all mean? Well, it means that if we take the reciprocal of the gamma function, now I'm taking the reciprocal of something non-zero, so this is actually holomorphic. And the only zeros are from the poles of gamma, so the only zeros are 0, -1, -2, and so on. Okay, so that suggests that we can do this factorization trick like with the sine function. Okay, so the 0 at z equals 0 gives us a factor of z, and then we'll have a factor of 1 plus z over n for every positive integer n. That will give us the other zeros. Okay, now this is wrong for a few reasons. First of all, this does not converge when you actually multiply it all out. For example, if z equals 1, you get into some very bad problems because you get 2 times 3 halves times 4 thirds, and so on. And the partial sums of that are just the positive integers. Well, the integers starting at 2. So that blows up. Okay, so to fix this, what you can do is include a correction term that will shrink these factors without introducing any zeros. So one way to do that is by multiplying by e to the minus z over n. Now, e to the minus z over n starts with 1 minus z over n, and then some other terms. So when you multiply by 1 plus z over n, now the first terms are 1 minus z squared over n squared. And that's good because that will actually converge no matter what z is. Now this still isn't quite right. We have a function that is holomorphic. It makes sense, which is also good. The zeros match up, but there might be some extra factor here. Well, and there is. But at least we know that that factor cannot have any zeros, and it has to be holomorphic. Okay, so what does that mean? Well, if we have a holomorphic function that's never zero, we can take the log of it. So it has to be e to the power of some holomorphic function on the entire complex plane. Now the last detail is to figure out what this g function is. To do that, we can first think about the relationship between gamma of z and gamma of z plus 1. So if we think about what gamma of z plus 1 over gamma of z is, we know that's going to be z. But let's write out what it is in terms of this product. Okay, so the 1 over gamma of z factor gives us the same product from before. And then we have the reciprocal of that, and with z replaced with z plus 1. Okay, so z plus 1, e to the g of z plus 1, product of 1 plus z plus 1 over n, e to the minus z plus 1 over n. Now that looks bad, but there's quite a lot of cancellation. So we'll end up with z over z plus 1 times e to the g of z minus g of z plus 1. And then we have the product. Now it's 1 plus z over n over 1 plus z plus 1 over n times e to the 1 over n. Now that still looks bad, but we can do some more simplification. So there isn't much we can do with the initial bit yet, but in the product we can multiply the numerator and denominator by n. And now much of this is going to telescope. So we'll have 1 plus z over 2 plus z, 2 plus z over 3 plus z, and so on. Okay. Now, okay, to make this rigorous, I'm going to have to take a limit. Okay, so I'm starting with 1 plus z in the numerator, and then everything will telescope up to n plus 1 plus z. And then I have e to the 1 plus a half plus a third, and so on up to the nth term. Okay, now the factors of z plus 1 cancel. And, well, I can write that as just e to the power of the nth harmonic number over n plus 1 plus z. Okay, now as n goes to infinity, the harmonic numbers behave like log n plus the Euler-Mascheroni constant. So when we exponentiate, we get e to the gamma times n. So in the limit, the n and the n plus 1 plus z cancel, and I get just e to the gamma. Okay, so after all that, we get z e to the g of z minus g of z plus 1 times e to the gamma. And now remember, this was gamma of z plus 1 over gamma of z. And we know that that's just z. Okay, so that means that this term here is 1. So we have 1 over the gamma function equals z e to the mystery function g of z times the product of 1 plus z over n e to the minus z over n. And now we know that g of z plus 1 minus g of z is the Euler-Mascheroni constant. Okay, so now the nicest possible function that could satisfy this is just gamma z, which is what it turns out to be, but proving that takes a little more work. So I don't think I'll get into that because it's a little bit tedious. But one way of proving that it really is gamma z is to look at the derivative of g. So when we differentiate, we get g prime of z plus 1 minus g prime of z is 0. So g prime is holomorphic. Well, it's entire. It's holomorphic on the whole complex plane. And it's periodic. Okay, that's a good sign because if you have a periodic holomorphic function, if you can show that it's bounded in some strip, so some strip of width 1, then the periodicity tells you that it's bounded on the entire complex plane, and then it has to be constant. Okay, so that forces g prime to be constant, and that tells you that g is linear. Okay, so by looking at what happens, for example, when z goes to infinity, you can show that g prime is bounded, and then that forces g to be just gamma z. Okay, so after all that, we finally end up with 1 over gamma of z equals z e to the gamma z times the product of 1 plus z over n e to the minus z over n.